Welcome back, everybody. In our last, most recent segments, we've been talking about work, and then more recently, the force applied by a spring. And now we're going to be getting into what happens if you have the force applied by a spring applied over some distance. Now, what's interesting about springs is that the force that they apply, the force, oh, you can do better than light green. The force applied by a spring is going to be a function of how much you displace it. So K times X. Remember that K is, we call it the spring constant, where it's a measure of the stiffness of the spring. It tells you how many newtons it feeds back with depending on how much you displace it. Okay? Well, our definition of work is force applied over a distance. Work equals a force times a distance. So what happens if we have a force that is dependent upon distance itself? That's going to be what we're going to be looking at this segment right here. But before we do, let's just remind ourselves about what happens with a spring. Okay, if right here is the equilibrium length of a spring, if it's at that length, it's not going to be applying any force. If you stretch it to position X, so we'll say this is position X right there, it feeds back with a certain force, which is whatever that is. What if you stretch it to 2 times X? 2X, so you stretch it all the way out here. It's not a very good stretch spring, is it? I'll do better like that, okay? Well, if you double the distance, 2X, you're going to have double the force. And so on. 3X, 3 times the force. So the more you displace it, the more force it feeds back. This is going to produce something interesting when we now plot force on the y versus position on the x. Now recall in the previous, when we talked about a constant force, let me just redraw this real quick here. With a constant force, force over distance, a constant force means that it did not vary as you went up. So no distance, no force. Increasing distance, increasing force. Well, with a constant force, you had simply this right here, and the force was the same over that whole distance. And you could find between displacement 1 and displacement 2. All right, that was our nice area right there, and that force times that distance, or that force times that displacement, gave us a nice square area where we could find the work. Now we're going to look at this varying force right here, starting at 0, and the more you displace it, the more it feeds back. And interestingly enough, the work that the spring does depends on that. And that's going to be this graphic right here. So, if you don't displace a spring at all, it feeds back with 0 force, right? 0 position, 0 force. If you displace it a certain distance d, or you could call it x, you can think of it like that, it's going to feed back with a certain force. Force by the spring, okay? But as you get it to that displacement right there, it's going to feed back. It's going to go from providing no force to a little bit of force to more force to more to more to more to more, and the force is going to get greater and greater and greater as you stretch that out to distance d or to distance x right there. So what's still true is that work equals force times distance. But if that force is a force of a spring, we need to keep in mind that the force of a spring is K times X, right? That's Hooke's law right there. The spring constant times the amount that you displace it times our distance. All right, well, distance is kind of the same measure as X, right? It's a measure of distance or length right there. So instead of calling it d, I'm just going to call it x as well. What's happening is this force is kx. Our horizontal value right here is just x distance. And so we have this area being basically the area of a triangle. How do you find the area of a triangle? Well, the area of a triangle is this area right here. It's 1/2 base times height, right? What's the base? That's going to be our distance d, or we've been calling it x, right? 1/2, so 1/2. Base is x. Our height is the spring force, right, which is kx. So if we put those together, the work done by a spring as you stretch it is 1/2 kx squared. This work, we say it's the area under the curve. Now again, our graph isn't curving, but it's also not a constant force either. It's not like before where it's straight across. It's an increasing force, so we've got a sloped graph right there. So the area under the graph, or the area under the curve, is the work that a spring does. And that is described as 1/2 kx squared. So we're going to finish out this segment with one more example involving the work done by a spring, and then we're going to call it a wrap. Okay? So example 8.7. Suppose a block has a mass of 1.5 kilograms. Okay, got it? And moves with an initial speed of Vi equals 2.2 meters per second. You know what? This isn't all that detailed of a problem. Let me draw this out for you so you kind of understand it. Okay? What's happening is there's a sliding block moving horizontally. All right? And it's going like, here's the surface right there. We'll call that, I'm going to erase this. Call that a wall. Surface and a wall. All right? And I'm having a hard time drawing straight lines. It's a little bit better. And a wall right there. What happens is we've got this sliding block, and it's moving with Vi equals 2.2 meters per second. Okay. So, and it's moving towards the spring, which is sitting here, kind of minding its own business, at the equilibrium length right there. Okay, so it's not compressed at all, but this box is hurtling towards it. All right? Well, what's going to happen if this sliding box moves towards the spring? Well, what's going to happen is that spring is going to compress. It's going to squeeze down because the box has moving energy. What do we call it, moving energy? It's kinetic energy, right? And it's going to, that moving box is going to cause that spring to squeeze down, and very temporarily that box is going to come to a stop. Now you've seen this kind of thing happen before. What happens if you slide something into a spring? The spring compresses, it stops, and then it shoots it back out, right? We know that's going to be what happens next, but very temporarily right here. We're going to say at this instant in time, this final velocity equals 0 meters per second. Okay, a little bit about the spring. The spring has a spring constant, the K, equals 475 newtons per meter. So it's a little bit weaker than the other springs that we've been talking about. Oh, and by the way, the mass of the block equals 1.50, or just 1.5 kilograms. Okay? We want to find the compression of the spring. That means this distance from here to here. And I'm going to call that x. And I'm going to call that x. Now we can call distance d. We can call it x. I'm going to call it x right now because in our equation for the work done by a spring, the distance is indicated by x. All right? We don't always call it x, which is why we call it d sometimes. But d and x are the same type of value. They're a measure of distance or length. All right, and that x right there is what we're solving for. X equals what? All right, well, we have this block moving with some kinetic energy, don't we? Kinetic energy initial right there, and that's where all you might say the energy is right now. But what happens when this sliding block moves against the spring? It does work against the spring. It compresses it. You know that if you have a spring and you squeeze it down, it requires work with your hands. So the work done, you could say either by the spring or on the spring, work done by a spring equals what? Well, we just defined that in our last slide. That was 1/2 kx squared. 1/2 times the spring constant times the distance it was displaced squared. All right, so we have this kinetic energy that the spring has. That the box has. That's 1/2 mv squared. But I'll just leave it ki right now. What kind of final kinetic energy does it have? What's kinetic final? Well, you can calculate it. You can calculate it. But if kinetic energy is 1/2 mv squared, in this case v final, what's that kinetic energy going to be? Well, its final velocity is 0, so that's going to be 0 right there. Our kinetic energy initial is going to be what is going to go into doing the work to compress the spring right here. So before I mince any more words, let's just write out the work kinetic energy theorem. The net work equals the change in kinetic energy. Well, what's the net work that was being done? Well, that was the work done by the spring, or on the spring. Okay? And our change in kinetic energy is always final minus initial, right? So that's going to be our final kinetic energy is 0 because the block comes to a stop. And you know what? I'm not going to put values in yet. I'm just going to put K final minus K initial. All right, and then we'll worry about our values. Now let's expand all these out. Work done by a spring equals 1/2 kx squared equals our final velocity. All right, well, that's our final kinetic energy. That's 0 minus our initial kinetic energy. That's going to be 1/2 mv initial squared, and we have that v initial. All we need to do is solve for our x right here, and we'll have the problem solved. All right. Well, what I'm going to do is, first of all, I'm going to ignore this 0 right here. All right, and I'm just going to say 1/2 kx squared equals negative mvi squared. Hey, what else do we see right here that we can cancel out or get rid of? These 1/2s, right? That goes away, and that goes away. So if we're solving for our x, our displacement, what we're going to do is we're going to take our k and divide it down, right? So we're going to say our x displacement squared equals mv initial squared divided by the k, which means that our x itself is going to be the square root of mv initial squared over k. All right, we got to this point by using the work kinetic energy theorem, that the work that is done is a result of a change, or in this case, a loss of kinetic energy. All right, so let's put our values in and see what we get, and that'll be it for this segment right here. I'll give myself a little more space. There we go. All right, so the mass is 1.5 kilograms. We're going to multiply that by the initial velocity, 2.2 squared, right? And the K constant of the spring is, by the way, I'm sorry, I call this the K constant sometimes because we call it K, but it's really called the spring constant, or the force constant sometimes, but I call it the K constant. That's 475 newtons per meter, right? And that goes in our denominator. So that'll help us to solve for our distance. Again, what are we trying to find right here? We're trying to find how far has this spring been squished down by the moving block when the block has come to rest right there. So let's put our values in and solve for it. Now I get a value of 0.12, oops, I'm trying to write with my laser pointer again, 0.12 meters, and that is 12 centimeters, if you want to think of it like that. Okay, so that's our displacement of our spring. All this was gotten by using our work kinetic energy theorem, setting the work that was done, in this case the work done by or on the spring, equal to this change in kinetic energy, final minus initial. Okay, that's example 8.7, a good application of the work done by a spring and equating that with the work kinetic energy theorem. Thanks for following along. I'll see you on the next one.